In the prior video segment, we looked at a solid model of a W12 by 50 wide flange beam. In this segment, we will construct an equivalent beam element model entirely within Simulation Mechanical, set up and run the simulation, and compare the results to the solid model's results. Begin by creating a new analysis model, ensuring that the analysis type is set to static stress with linear material models, and name the file. We'll call it W-beam. Go to the Draw tab of the ribbon and execute the Line command. Ensure that the Use as Construction option is deactivated. Beam elements must be actual FEA lines, not construction lines. The default coordinates of 0, 0, 0 are acceptable for the first endpoint of the line. Just press Enter to accept the point. Type 360 in the X input field and press Enter to set the point 360, 0, 0 as the endpoint of the line. Then close the line dialog and enclose the model using the Zoom Fit All command in the navigation bar. Set the element type to Beam. Then, double-click the Element Definition heading to begin setting the cross-sectional properties. There is only one layer in this part and therefore only one cross-section. Select the row in the Sectional Properties table and click the Cross-Section Libraries button. Let's choose the newest of the AISC beam libraries, specifically AISC 14.1 from the year 2013. Next, choose W from the Section Type drop-down menu. You can begin typing the name of the section to locate it more quickly, since the list of sections is fairly long. Choose W12 by 50. Note that the cross-sectional properties are listed in the middle of the dialog. Click OK to accept the settings and close each dialog. Double-click the Material heading and choose Steel ASTM A36 from the Material Library. In order to show the true deformed shape of the beam and to provide multiple stress calculation points along its length, divide the line into multiple segments. First, switch to Line Select mode and click the line. Then, click the Divide command in the Modify panel of the Draw ribbon tab. 60 divisions should be more than enough. Since the beam is 360 inches long, this number of divisions will produce 6-inch long segments, or 2 segments per foot of length. We can temporarily enable the Endpoint Vertices option in the View ribbon tab to confirm that the beam span has been properly divided along its length. Next, change to the Vertices selection mode. Pick the endpoint at the -x end of the beam span to apply a general constraint. Fix all degrees of freedom except for Tx and Rz. This will be the axially floating end of the beam. Next, pick the opposite endpoint and apply another general constraint. This time, fix all DOF except for Rz. This endpoint can rotate about the z-axis but cannot translate in any direction. Next, we need to apply a distributed load along the full length of the span. A convenient way of selecting all 60 elements is to click the part in the browser, then right-click and choose Select Related Lines from the context menu. Click the Beam Distributed Load command in the Setup tab of the ribbon. Note that the magnitude is specified in pounds of force per inch. The total load is 5,000 pounds and the span length is 360 inches. We can type 5,000 divided by 360 equals in the magnitude field, and the program calculates the load per unit length of 13.89 pounds per inch. Type -1 in the Y field to specify the direction of the distributed load, and click OK. Note that beam elements must be oriented correctly, since the line that represents the cross-section cannot dictate on its own whether the beam is horizontally, vertically, or otherwise oriented. The default surface number for a line is surface 1, and we did not change the surface number when we drew the beam. In Simulation Mechanical, lines on surface 1 orient the beam such that the depth of the section, local axis 2, is in the global y direction. This diagram and table from the program Online Help shows the correlation between the surface number and the K-node location used to orient the cross-section. You can also custom define the orientation point for beam elements. Let's change the model viewpoint to be consistent with a Y-up drawing scheme. Now the load acts vertically downward as viewed. The simulation is ready to run. Beam element models solve very quickly due to the low element count, and they avoid the complications encountered in producing an adequate brick midplane or plate shell mesh. Notice the beam element, though just a line, is rendered in 3D within the results environment. The shape data comes from the predefined properties in the beam cross-section libraries. Note the resultant displacement of approximately 0.27 inches, which is within 1% of the brick model results. Next, look at the beam and truss worst stress results. The maximum stress is approximately 3,505 psi, which again is within a 1% tolerance when compared to the von Mises stress results of the brick element model. In addition to hand-building beam models within Simulation Mechanical, the lines can also be drawn in a separate CAD program and imported as Inventor Sketches, DXF, or IGES wireframe geometry. Finally, another complication you may encounter in FEA work is when the distorted shape of a structure under load causes the contact conditions to change. To handle this condition, do one of the following. Define surface contact between parts so that they are free to come into contact, slide, or separate relative to each other. Additionally, a nonlinear analysis type can be used to support rigid body motion and large displacements. Focus on the phenomenon of interest by limiting the range of motion using additional boundary conditions. Of course, care must be taken to ensure that you are not exaggerating the stiffness or strength of the structure and therefore underpredicting the stresses. Focus on the area of interest by removing components from the assembly. Concentrate on the critical components and loads, neglecting less important phenomena. Of course, sound engineering judgment must be used to ensure reasonable and meaningful results are produced. In summary, we have discussed common complications encountered in FEA, including how to handle thin features, small features, extreme aspect ratios, such as beams, and contact conditions that change during the analysis. The two-part video demonstrated a comparative analysis of a beam using 3D solid and 1D beam elements. We hope that you find this information useful. Thank you for watching.